All right, let's get into it. We all learn how to multiply numbers back in grade school, right? But what about vectors? These aren't just simple numbers. They have both a size and a direction. So we're going to break down the two really powerful and totally different ways you can multiply them.
I mean, think about it. What does it even mean to multiply two directions? It's a way deeper question than it sounds. Because with vectors, it turns out there isn't just one answer. Multiplying directions can either tell you how much they agree, or it can create a brand new direction that you didn't even have before. And for those two very different jobs, we have two very different mathematical tools. So first up, we've got the dot product. The absolute best way to think about this thing is as an alignment meter. It's super simple. You give it two vectors, and it answers one question. How much is this vector pointing in the same direction as that one? Now, when you look at the formula, you'll see something really important. The result of a dot product, it isn't another vector. It's what we call a scalar, just a plain old number, no direction. And the secret sauce here is that cosine theta. The cosine of the angle between the vectors basically acts like a percentage of alignment. If they're pointing the same way, cosine is 1, 100%. If they're totally unaligned, it's 0. It literally just measures how much they agree. Okay, to really get a gut feeling for this, let's use a fantastic analogy. Forget the math for just a second, and picture a shadow. The dot product, at its heart, is all about how one vector casts a shadow on another. Let's look at this first scenario. Imagine the sun is right up there, directly overhead. If our two vectors are pointed in more or less the same direction, one of them is going to cast a really nice long shadow on the other. This gives you a positive dot product. And the more aligned they are, the longer that shadow gets, and the bigger that positive number becomes. But what happens when the vectors are pointing away from each other, at an angle bigger than 90 degrees? Well, now that shadow gets cast backward, in the complete opposite direction. This is what gives us a negative dot product. It's basically the universe's way of saying, nope, these two are in opposition. And this brings us to the most critical case of all. What if the two vectors are perfectly perpendicular, at exactly 90 degrees to each other? Well, then one vector casts no shadow at all on the other one. It's like trying to see a flagpole's shadow at high noon. It's just a dot. The dot product is exactly 0. And this is a huge deal. If you ever need to know if two vectors are at right angles, you just check if their dot product is 0. It's the ultimate test. Okay, so if the dot product answers the question, how much alignment, our second tool, the cross product, answers a completely different one. Which way? Now we're leaving the world of shadows and single numbers, and we're entering the world of 3D orientation. So unlike the dot product that gives us just one number, the cross product takes two vectors and spits out a brand new third vector. And this new vector is really special. Its direction is perpendicular to both of the vectors you started with. It's how you can find a whole new dimension, basically popping right out of the flat plane that your first two vectors were sitting in. So how in the world do we find this new direction? It's actually really intuitive, and you can do it right now with your own hand. It's called the right hand rule. Just take your right hand, point your fingers in the direction of the first vector, and then curl them toward the second vector. Whichever way your thumb is pointing, that's it. That's the direction of the cross product. It's like a physical cheat code built right into the math. So, let's just quickly put these two side by side. The dot product gives you a scalar, a number, that tells you all about alignment. Its big test is checking for perpendicularity. The cross product, on the other hand, gives you a whole new vector, a brand new perpendicular direction. And its main test is for parallelism. If the cross product is 0, it means your vectors are on the exact same line. Two different tools, two totally different jobs. All right, so we've got these cool kind of abstract tools for measuring alignment and finding new directions. But now let's see how they actually let us build and measure real geometric shapes out in space. Turns out the cross product has another cool secret. We know its direction comes from that right-hand rule, but what about its length, its magnitude? Well, that's not random at all. The length of that new vector is precisely the area of the parallelogram that's formed by your two original vectors. So it's not just finding a direction, it's actually measuring a 2D area in 3D space. How cool is that? And this is where things get really, really elegant. So we've got a tool for finding area, that's the cross product, and we've got a tool for measuring alignment or projection, that's the dot product. So what happens if we use them together? We get volume. It's a beautiful two-step process. First, you take the cross product of two vectors. That defines the base of a 3D shape, and its magnitude gives you the area. Then you take the dot product of that new area vector with a third vector. What that does is it projects that third vector down, basically measuring the shape's height. And base area times height, well, that's the volume of this slanted 3D box, which is called a parallelepiped.
So yeah, we've seen how these tools can build shapes. But the thing that makes them truly powerful, the reason we're talking about them, is that this isn't just some abstract math game. This is the fundamental language that physicists use to describe how forces and motion actually work in the real world. For instance, in physics, the amount of work done by a force is calculated with a dot product. Why? Because you only care about the part of the force that's aligned with the direction you're actually moving. And torque, the force that makes things spin, that's a cross product. Because the force you apply, the lever arm, and the direction of rotation are all happening in mutually perpendicular directions.
Which, it leaves you with a final thought. From the way an airplane wing generates lift to the behavior of magnetic fields, these mathematical rules are hiding everywhere, just beneath the surface. It really makes you wonder, how many other things in the universe are secretly being governed by the simple elegance of a shadow and the simple twist of a right hand?